Hi, my name is Mehdi Amini, and I'm here with Riddle today to walk you through this MLIR tutorial. This tutorial is intended as an introduction to MLIR and does not require prior knowledge. We'll sometimes compare to LLVM though, so having experience with LLVM may make it easier to follow. We will start with a high-level introduction to MLIR before getting into some of the internals and how these apply to an example use case. Here is the overview of this tutorial session. We will start by making up a very simplified, high-level, array-based DSL. This is a toy language solely for the purpose of this tutorial. We then introduce some of the key core concepts in MLIR, operations, regions, and dialects. These concepts are then applied to design and build an IR that carry the language semantics for the toy. We illustrate other MLIR concepts like interfaces and explain how this framework fits together to implement transformations. We will lower the code towards a representation that is more suitable for low-level optimization and cogen. The dialect concept in MLIR allows to lower progressively and introduce domain-specific middle-end representation that are geared toward domain-specific optimization. For CPU cogen, LLVM is king, of course, but one can also implement a different lowering in order to target accelerators or FPGA. So what is MLIR? From a high level before getting into the nitty-gritty. MLIR is a toolbox for building and integrating compiler abstractions. Essentially, we aim to provide extensible and easy-to-use infrastructure for your compiler infrastructure needs. You are able to define your own set of operations, your own type system, and then reuse all the MLIR path management, diagnostic infrastructure, multi-threading, serialization and deserialization, and all the other boring bits of infrastructure that you would likely have to build yourself. The MLIR project is also batteries included. On top of the generic infrastructure for manipulating the AR, multiple abstractions and cut transformations are integrated. The project is still young, but we aim to ship various cogen strategies that would allow to easily reuse end-to-end flow to include heterogeneous computing, for example, targeting GPUs, orders, accelerators, into your DSL or your environment. The multi-level aspect is very important in MLIR. Adding new levels of abstraction is intending to be easy and a common task when using MLIR. Not only this makes it very convenient to model a specific domain, it also opens up a lot of creativity and brings a significant amount of freedom to play with when playing with compiler designs. It's really a lot of fun to design a compiler with MLIR. So MLIR allows for various abstractions to freely coexist. This is a very important part of the mindset. This enables abstraction to better target specific areas. So for example, people have been using MLIR for high-level general purpose languages like Fortran. The Fortran compiler in LLVM, flang, is designing its own high-level IR with MLIR. MLIR has also been leveraged in machine learning framework like TensorFlow, ONNX, or XLA to process machine learning graphs, which are linear algebra operator processing multidimensional array with usually dense or sparse computations. It also includes quantization, cross-host distributions, and other specificity of ML frameworks. At a very, very different level of abstraction, the CIRCT project, which is an incubator project in LLVM, is actually using MLIR to build tools for hardware design. Again, with a very different mindset, TFRT and ERE are two different runtime projects that have been using MLIR to model some of the runtime primitives they expose. Finally, MLIR intends to enable better research in compilers, and some projects have been exploring it by modeling concurrency or functional programming, and hopefully it will help many other projects to advance the field of compilers. We also have inside MLIR an original uses for MLIR. it's about optimizing MLIR itself. We have a meta IR, which allows to manipulate the IR with the compiler itself. So it's kind of a meta IR for manipulating MLIR. It's a bit complicated, but it's also very interesting. Some of the users of MLIR are referenced on the website at this URL. If you're interested to learn more about them, I invite you to visit this page and visit the individual project pages. All right, let's look a bit more at our example today that we will use to illustrate MLIR concept. The high-level language that we will use is a mix of scalar and array computation, as well as I/O, limited to printing, actually. The basic is to do operations on multidimensional arrays, but also to have generic functions and perform shape inference. We will limit ourselves to a very limited set of operators for the sake of simplicity. So here is an example of a function in this language. And this function can be thought of as a C++ template where we will deduce the actual types of the operands at call sites. At every call site, we'll need to specialize the function. And then we will propagate the type throughout the function. Again, for the sake of simplicity, inside the language itself, we will limit ourselves to value-based semantic and SSA, so single static assignment. Variables are written only once. LLVM knows how to transform variables into SSA, and for the sake of simplicity, we're not going to re-implement the SSA formation. Let's just get it from the source language. We're not going to implement a lot of operators on those arrays, just the minimum amount to showcase MLIR's transformations. All right, and the language will also support reshaping arrays by explicitly specifying the shapes at the declaration time. And finally, we will only support double precision floating points for the sake of simplicity again. So how are we going to build a compiler for Toy? Well, let's look at existing successful compilers. Clang, for instance, is building an AST for C, C++, performing some transformation on the AST, like template instantiation, some context per folding, and then it lowers the AST directly by emitting LLVM IR. That's been proven to be a very successful strategy when using LLVM, and many compilers have been built this way. Now, when you need to implement some language-specific transformations, you want to benefit from the high-level semantic of the language that you're losing when you go to LLVM IR. You can try to extend LLVM IR with more intrinsics, more metadata, but this is fairly brittle. So in the last decade, languages like Swift or Rust have been developed with a high-level IR to manipulate those. And mlir takes inspiration from this to make it easier to build new level of abstractions. So we're not going to model Toy and our compiler on Clang. We're not going to try to make transformation on the AST. It will make the AST much more complex. It would require us to build a new heavy infrastructure to support the transformation and the analysis on the AST. This is not very convenient. We'd rather have an SSA-based IR. And so what we're going to do is to build this IR with mlir. This IR is going to be specific to Toy. We don't want to implement all the infrastructure. That's where mlir is going to really shine. Hopefully, the mlir ecosystem should help us also to target accelerators. If we are in compute-intensive world and HPC, accelerators are really ubiquitous nowadays. And mlir intends to make it much more easier to target heterogeneous environments. So I'm talking a lot about abstractions and levels of abstractions. In mlir, it's all about dialects. And you're going to hear a lot about dialects. And I'll come back in details into what is a dialect. What it means mostly, and what you should expect to get when you have dialects, is that those are modeling abstraction level and that those are composable and reusable as much as possible. It's not the case for all of them. For instance, if the abstraction we're going to implement for Toy is unlikely to be reused for anything else. However, there are dialects that are designed for reusability. For example, in mlir today, there is dialect for OpenMP and another one for OpenSCC, which are standard to perform parallel programming. And so hopefully, the ability to reuse those dialects means that if in the future we want to extend Toy to benefit from parallel computing using OpenMP primitives or OpenSCC, we should be able to reuse those abstractions that are existing in mlir. And so the OpenMP modeling that exists in mlir could be reusable by Toy, just like it's going to be used by the Fortran compiler or by other compilers. All right, let's look a bit more into the key concept that exists in mlir. So in mlir, the most basic component of the IR is the operation. And it's a bit different from the LLVM instructions. In LLVM, there is a predefined set of instructions. Every instruction in LLVM has its own C++ class with its own data member and its own modeling. It's not the case in mlir. In mlir, operations are all sharing the same structure that we have to fit in. But the structure is very extensible, as I'm going to show you. Operations can model anything from x86 adding to registers operation to let's execute a remote RPC task. And an operation itself can even represent an entire loop nest. And I'll come back to this later with a good example. Let's look at the structure of the IR. So what you see on the screen here with a lot of colors is actually the textual IR. Just like in LLVM, when you print the bit code in assembly format, mlir has a generic assembly format. And every operation in mlir can be represented through this generic format. That makes serialization and deserialization really simple. So what are the elements that define an operation? We have an isomorphic representation between the in-memory representation and the textual generic form. So it's very important that we follow this along and that we understand that there is this one-to-one mapping. First, what uniquely identifies an operation is its name. So you have the operation ID that is prefixed by a dialect and as a namespace. And this name, dialect plus op ID, is unique and makes the operation name. An operation produces SSA results. LLVM instructions are generating one SSA value at most. In mlir, operations can generate many results. This operation here, for instance, has two SSA value returns. So there is only one name. We named the results, the set of results with one name here, but there are really two SSA values. After the operation name, in between parentheses, you have the argument lists. And this is a comma-separated list of SSA value. And you can see that there is the name of the SSA value, but there is also an index. And that's because since operation can return multiple SSA value, we need to distinguish them. Here, we're going to use the fourth results of the operation that produced input. After the list of arguments, or SSA value arguments, we have a different kind of arguments, which are attributes. Those are literal, constant, named arguments in some ways. They can be optional, they can be defined by the operation. They are a bit stronger than the metadata in LLVM because operation can require and really define the semantic of some of those attributes that can be specific for each operation. On the second line, we have the type of an operation. We use a functional notation. So after the colon, in parentheses, you have the type of the arguments. We need as many types here as we have arguments. In this case, we only have one. The type after a bang is followed by a dialect name and the specific serialization of the type has to be customized and interpreted by the dialect itself. It's opaque to mlir. After the row, we have the type of the results. Here we have two results, so we expect two types. Finally, on the third line, every operation will have a location. Most of the time, we don't print it for simplification, but it's always present in memory. Locations in mlir are fairly rich and extensible. Here we can represent that this operation corresponds to a call sites to a given function at a given place in the source file. All right, this is really all what makes an operation. And something to keep in mind when you define your own set of operation is that you cannot add more storage. When you define an operation in C++, you only specify what is allowed or not. You're gonna be able to specify if an operation returns multiple results or not, if it allows to take one or multiple inputs, what are the types of the inputs, and what are the attributes that are allowed. And everything is what you define when you customize and specify an operation. But we cannot extend it with more than what is shown here. Well, actually, there is one more thing. So let's look into regions on the next slide. On top of those elements, operations can also hold a list of regions. So the concept of regions doesn't have any equivalent in LLVM. In LLVM IR, you have a first-class concept of functions, and the body of a function is actually a CFG. The CFG is the control flow graph, which is a chained list of basic blocks. In MLIR, we start everything is an operation. Even a function is an operation. Operations can have a region. A region is nothing else than a list of blocks, which can maybe model a CFG. So this is how we actually model functions in MLIR. It's going to be an operation, and the body of the function is just a region attached to the operation that defines the function. So I'm showing an example here. At the top, we have this operation here that returns 2 results and takes 2 operands. And then after the parentheses and the curly braces, we have here a region. And I did some color to make the structure more clear. But inside this region, what we have is one block here with the caret and the name block, and another block here. Those blocks are both having a list of operations. Here we have one operation nested here, and another operation here. And in the other block, we have a single operation here. And now you can see that this operation that is nested in the block, that is nested in the region, that is attached to the outer operation, can itself contain another region with an operation. So the IR is recursively nested. And that's a whole new dimension in the design that doesn't exist in LLVM. Makes the IR very extensible and very powerful. I'm going to show you very soon how we use region to model loop structures, and in particular, how it enables affine optimizations. All right, and that's it for operations and regions and blocks. And with this, you can understand the entire MLIR IR because there's nothing else. The outer module is not a first-class concept in MLIR. It's just an operation like any other. A module is going to have a single region attached to it. This region has a single block, which is a list of operations. Those operations are the equivalent of the global values in LLVM. And so you have an operation to define new function. Function that are not declaration, that are definition, will have a body. This body is another region, which is a CFG again. All right, so it's very generic, very regular. It makes everything very nice to traverse. You don't need to special case anything when you get this structure in your mind. All right, the structure is very generic and you can model everything with it. Now, there's a catch, because so far we can model things like this. We can have this main function where we have a toy.print operation, except that it's a bit broken. Like if I write this today, I can round trip this through mlir opt. It will load it. It will consider it as an opaque operation because it doesn't know anything about it. But mlir will happily model this. It's broken because print should not produce a value, right? Here we see that there is a results tensor, and we see the SSA value that is created. It doesn't make sense for toy. Our prints built-in is supposed to take an argument. There are no arguments here. That should be invalid. We shouldn't be able to model this in the IR. So how are we going to solve that? We're going to solve that by introducing dialects. Yeah, we absolutely don't want MLIR to be the JSON of compiler IR. We want semantics associated to operations. So what is a dialect? So again, you'll hear a lot about dialects in the MLIR ecosystem. You can think of a dialect in compiler IR like you think of a C++ library in software. At minima, it is a namespace where you're going to group a set of types that you're going to define, a set of operations that operate on this type, or operates on types defined by other dialects, and a set of custom attributes. So just like a C++ library where you define your classes, your method, etc., the dialect is your own IR library. By defining this set of types and operation, you can define a closed set that has a well-defined semantic and that you can manipulate. The dialect is loaded inside the MLIR context and extend MLIR by hooking into the framework. So MLIR exposes various hooks that can be implemented by the dialects and the operations that you define in the dialect. Like, for instance, invariant verification. So just like the LLVM verifier is ensuring that your IR is well-formed, the MLIR verifier will delegate to your dialect the verification of the op you define. And that's how we're going to address the toy print case that we had before by registering our dialect and registering invariants that we're going to write for the print op. MLIR will be able to detect when the IR is invalid. So dialects are supposed to be really cheap. You create one like you create a new library. There are roughly 20 dialects that comes bundled with MLIR, but there are even many more that have been defined by MLIR users. Our internal users at Google have defined over 60 dialects so far. So something else that you're going to see when you look at MLIR examples is that the IR doesn't always look like the generic form I showed you before. That's because dialect author can also customize the printing and the parsing of operations and types. That helps making the IR much more readable. So an example of nice syntax and advanced semantic modeling at the same time using region is shown here with the Affine dialect. So the Affine dialect is modeling polyhedral loop nests and a bit more, but let's simplify it. We see that here you have a function with nested loops, and inside the innermost loop you have a conditional with some sort of equation, linear equation, actually. And this is important for polyhedral tool because it ensures that the loop itself and the iteration space can be analyzable and transformable with some mathematical framework. Now, how is it represented in MLIR? As I told you earlier, everything in MLIR is an operation. So this for loop and the top level for loop that you see here is actually an operation. And this is just a sugared view for everything that you can store in an operation. And the open curly braces here will correspond to a region attached to this outer operation. And so the region is a nested CFG, which is going to contain here a single block and a single operation here, which is another affine for, which again is going to have a region attached to it, which is again another level of nesting for a CFG. If you think about it, it's the same structure that you have in any structured programming language. And the IR allows you to model this. And then you have the conditional inside. So it's all nice and easy to read, but this is just sugar for the assembly printing. When you are manipulating those concepts in memory, you need to keep in mind the generic form of operations. So there is an option, a command line option, to print the actual generic form for any piece of IR. And so we could take this example, feed it to MLIR opt, and print it with the generic form, disable the custom printer for the Affine dialect. And it would actually look like this. And here you can see what I described earlier, where you have this outer Affine for loop with a list of attributes, which is less nice to read, but represents the actual iteration space. And you have the nested for here. And so we can see that let me see. So it's an operation that takes no arguments. There's a list of attributes. This is the type. It takes no arguments, there's no results. And then after the parenthesis, we have the inner region. So we have a basic block. Basic blocks in mlir takes arguments like Swift instead of having phi nodes like in LLVM. I won't get into the details here, but you can think of those as phi nodes. And so this is for the loop iterator. And then you have the nested for, and you have again a region with another basic block in this region, again nested. And you have the affine if, the conditional, where the condition is this set that references this set defined here. And you can see here we have the linear equation that was nicely printed, collocated with the if, but here it's defined as a global symbol because that's how it's represented in memory in mlir. All right, and so this generic form here is actually more illustrative of what you manipulate in memory. It's really important to keep this in mind, that this is what you manipulate. All right, another example of dialect with a custom printer is LLVM. We can model LLVM IR as a dialect. It is actually implemented in mlir. You will find the LLVM instructions and types prefixed with the LLVM dot dialect namespace. It's not feature complete right now. For instance, it's missing inline assemblies or block addresses, those kind of things. But it defines enough of LLVM to support the common needs of DSL-oriented cogen. I will show you an example of this later. There are also some minor deviation from LLVM IR. For example, because of mlir structure, constants aren't special and are instead modeled as regular operations. And that's it for the mlir internals. So I'm gonna now give the prompt to River to introduce you to the Toy IR and how those concepts can be applied to Toy. River, up to you.
Thank you, Mehdi. My name is River, and I'll be giving a bit of a deeper dive into how we can map Toy into mlir. So for Toy, we're going to define a dialect because that is our unit of abstraction in mlir, and we're going to do this declaratively. Doing things declaratively is kind of at the root of mlir because it helps remove a lot of boilerplate and also helps us add some things that are really integral. So if we look over at our declarative specification for the Toy dialect, it's going to be done in TableGen, which is a kind of textual generation language almost in LLVM. So we're going to have a few components here. So we'll have a summary and description, which is kind of a documentation for what our dialect is, and we'll be able to actually generate markdown from this description, and this applies to all of the different declarative things that we define in mlir. And next is kind of the root of what a dialect is. So as Mehdi mentioned earlier, a dialect is really just a namespace that collects various different abstractions together. The final aspect is more for the generation of it. So C++ classes are what you would interface with in your actual compiler. So all of the declarative dialect specification will generate the C++ class that you would then interface with. And the C++ namespace on the right-hand side is where the different classes will be generated in. Once we declare the dialect, we're going to start filling it with different things. And one of those is our operations. So if we take this toy example here, we have a main function, we have some variables, and then we call this generic function, which does 2 transposes and then multiplies the result, and we'll print the result. So if we first take a look at this multiply transpose function, let's kind of imagine what it would look like if we just translated it straight to an mlir syntax without thinking about registration. So we have this function, and it has a few arguments and produces a result. And inside of it, we pretty much just map what in our toy language we have here. So we have 2 transposes, we multiply them together, and then we return the result. So for types here, we're actually using the built-in tensor type in mlir because it represents everything that we need it to. It has support for dynamic shapes, it has support for static shapes and our multi-dimensional arrays, and it supports our floating point 64 element type. We could define our own toy type and represent it that way, but for the sake of the tutorial, we'll just use the built-in for now. And then, of course, we're using the built-in function as our container here. So we're looking at the main function. It's very similar. Toy doesn't have a concept of memory, perhaps, for variables. So when we're defining our variables, we have a constant, and we'll reshape the shape of the constant into what the variable was defined in. We'll call our generic function, and then print the result, and then we'll return. So very similar to previously. So for each of the constant operations here, the toy.constant, you'll see that we have our value is an attribute, and we're actually using this dense elements attribute to represent the constant metadata. So dense is this built-in attribute that makes storing contiguous arrays much more efficient. So this should show kind of what a generic syntax for our toy operations will look like. But we want to actually define them because we get a lot of power from the definition. So we're going to do this declaratively, similar to how we did for dialects. So we see here how we're defining this constant op that inherits from this toy op. And this toy op base class is effectively just this simplistic thing that sets the dialect for the toy op. So it's not much detail to remove here. So very similar to the dialect, we want to be able to define our summary and description because documentation is a very, very important aspect of doing things generically and declaratively. And of course, all of this generates Markdown, and you can see it on the website, actually. Then we come to the arguments and results of an operation. And an argument is either the constant metadata attribute or an SSA value operand. And a result are the SSA values that an operation produces. And among the various different other aspects an operation can have, we're also going to add additional verification to make sure the semantics of the operation are correct. And we say additional here because if you actually look at the arguments and results, you'll see some constraints already specified next to the name. So for example, our attribute value, we want to ensure that it's actually a dense elements attribute, that's floating point, that everything is proper here. So these constraints will already generate verification automatically because of the specification. So we say additional when we talk about verification logic here, because a large portion of the verification of the operation is already generated for us. So it's only the special properties of the operation that are not already taken care of, either via constraint on the argument or result, or via trait, which we'll talk about later, that we actually need to specify here. So similar to dialects, this specification is going to generate a C++ class that we'll actually interface with in our source code. So this provides a variadic amount of benefits, removes a huge amount of boilerplate, and provides a lot of niceties, such as really nice named accessors for our attributes and operands that we don't have to define ourselves because we can just generate it. So once we've specified our operations for our toy dialect, we can revisit our example before and now see that things are properly being verified. So it's no longer just a large JSON string. We actually have semantics in the IR now, and they're being properly verified for our print example here. So we've been able to define our dialect, define our operations in this declarative way, and they exist in our source code, and we can round trip IR, but we're defining an abstraction for a purpose. We want to be able to do some high-level transformation or analysis that takes advantage of the abstraction that we're defining. So we'll look at some high-level transformations in the context of toy that really highlight this. So if we're talking about doing transformations in MLIR, we have a very strong tendency to do things generically. Reusing code is a very, very integral concept for the infrastructure. And one of the ways that we do that is with this mechanism called traits. And traits are effectively just mix-ins that add additional functionality, properties, verification for a specific entity. So that could be an attribute, an operation, or a type. And often the additional functionality, the property, is just the presence of the trait or not. And we can see this in some of the examples of how traits are used. So we can specify some mathematical properties such as, is an operation commutative, is it associative? We can define more structural properties such as, is this a terminator for a block? And this also goes down to the lowest level. For example, the accessors and verification for even the amount of operands that an operation should have. are handled via traits. So the actual definition of these op classes is very simplistic, and we just reuse the traits to make sure that we're not defining the same logic over and over again. So traits are a great way for adding new properties, functionality to an operation or other entity. But if we want to do things generically and opaquely, we want to be able to access that information. And we access this information opaquely via interfaces. So interfaces are basically just abstract classes that we can use to manipulate these entities opaquely. So they're just a group of methods with an implementation defined by an entity. But they're not C++ inheritance-based abstract classes. They're more akin to something like interfaces in C#. So the actual implementation will be specified by the entity, but we might not use virtual inheritance to actually do the implementation. We'll see that in a bit. So the interfaces are a really, really strong cornerstone of extensibility in MLIR because they remove the need for the transformation to actually enumerate or know about all of the specific entities. If you've ever written a transformation in an infrastructure that's not generic or extensible, usually you might have a very large switch statement or something that enumerates all of the possible operations that you might care about for a specific piece of a transformation or analysis. So interfaces are frequently defined by the transformations that we want to perform. Because we're accessing properties, something needs to know or want to know about these properties. So a transformation will take apart the various aspects that it actually cares about, the properties that it wants to know, aside from the general algorithm, and we'll put this in an interface so that we can make it reusable across many different dialects, aside from the one that we're just implementing. So from some examples we'll see for the context of operations, one large example is something like the call graph. So a call graph connects calls with things like functions or callables. So in LLVM, for example, the call graph is composed of calls like call instruction or an invoke instruction and a callable of a function. But MLIR is very, very extensible. The amount of semantics that we can represent are much larger. So a callable operation in MLIR might be a function. It might be a lambda that represents a function body inline with captures. So there's many different ways that you could specify something as a callable in the context of a call graph. And the same concept applies to loops. Many different loops in MLIR might have various different structural restraints or constraints on various semantics or properties that allow for more expressive either optimization or analysis. So we have all of these different operations that effectively boil down to the same core set of properties that we want to expose to transformations. And then we have something more smaller scale with side effects. So you would obviously want to know if a specific operation reads from memory, writes from memory, does it allocate memory? And we can do this opaquely. We don't need to know, is this a store op or a load op? We can just ask it its properties directly. So let's look at an example transformation problem that we might have in Toy. And we'll use this to kind of frame how traits and interfaces are used. The problem is a bit fake for the tutorial sense, but it's an important one. So shape inference. If we look at our generic functions that we have in Toy represented in MLIR, all of the Toy arrays or tensors are dynamically shaped, but we want to make them statically shaped. It'll make some cogen and optimization a bit easier. It's also tutorial friendly to cogen static shapes versus dynamic shapes. So how are we going to do this? We could do an interprocedural shape propagation analysis. That's one possibility. We could specialize the generic function for all of the different call sites that call it based on the shapes of the operands. That's another example. Or we could take the easy approach from the tutorial sense. We could just inline everything, because interprocedural analysis is hard and inlining everything is the best result, of course. So if we're going to write an inliner, it's a very common transformation a lot of compiler stacks have, but the actual mechanics behind it can get very complicated. There's a lot of different legality constraints. There's different ways to do it with cost model and traversing the call graph, etc. So it's actually kind of complicated at the core of it. But thankfully, MLIR already provides an inliner pass that is generalized. So it has taken the core properties it needs to know about what it's inlining and put those via interfaces. So if a dialect wants to take advantage, it doesn't have to implement all of this complicated logic. It just has to implement the specific hooks that the inliner needs to know to do its job. So for the context of toy, we'll need to provide things like legality, for cost model, a few key transformations here and there, and we'll need to expose our call to the call graph. We don't need to worry about the callable because we're using the built-in function operation, which already is exposed to the call graph for us. So here is kind of an example of how the inliner exposes the properties it needs to a specific dialect. The details here don't really matter that much. What's important is to take away what an interface or how a transformation exposes what it wants to know via an interface. So one of these mechanisms is that you want to query specific information. So the inliner might ask a dialect, hey, is it okay to inline this operation into this region or this destination? For toy, it's always legal because that's the simplest. So we might want to get some analysis information. A second example is that we might want the dialect or entity to perform part of the transformation for us, some very minute specific aspect that requires that semantic knowledge. So for this example, we might have, we have our return operation in our function, but when we put the body of the function into the call, we need to know how to resolve what happens with the return. So that connecting control flow is something that toy only knows about because toy return op and how it connects with the function is unique to toy. So the inliner will dispatch to toy to handle that transformation for us. And it's a very similar example is with a call conversion. So if you think about toy calls pass in maybe static shapes, maybe dynamic, but the functions for generic toy take in dynamic. So when we're inlining, there's this type mismatch. Inliner wants toy dialect to take care of this transformation. It recognized a situation and it wants toy to make sure that the transformation becomes legal. So this is just a large example of how if we implement these interfaces, the inliner will take care of us. So we want to expose the generic call op to the call graph. So this is, as we mentioned earlier, the call graph is exposed via these interfaces. So for calls, this would be a call op interface. So we attach this interface to our declarative specification of the generic call. And in our declarative specification, this comes right after the mnemonic or the name. So we have this nice utility, declare op interface methods, and that'll just add the method declarations to our op class that gets generated. So we just have to provide the implementation. So in our call op, the interface for the call wants to know a few things so it can properly expose itself to the call graph. So it might want to know what the callable for this call is. And for our case, that's just our reference to the callee. So a symbol reference is just kind of a string reference to a specific operation. And you can find more details about that on the website. And then the last aspect is what operands are being passed to the callable from the call. So when you call a function, what are the arguments to that function from the call? So we expose these interfaces to the infrastructure. And that's all it needs. It takes care of the rest of the transformation because it doesn't need to know any specifics other than the ones that we provided. So if we take our example of our function in our transpose generic function, we can just inline immediately. And you'll see that some of the operations have generated casts because of our mismatch in our calls to the function. So now that everything's inlined, we need to actually do the shape inference because we have these classes laying around, and now we need to implement some intra-procedural shape inference algorithm. The algorithm here is not really important. What's important is that when we're defining a transformation in the opaque sense, we can think about what properties we actually need to know. And for shape inference, if we look at the example below, most of it is kind of just a generic traversal algorithm. The only really interesting part is how it actually does the shape inference. And for this, we could just use an interface. And if we use an interface that makes our pass independent, that means that it's reusable. Other dialects can use it. So we can really just empower the infrastructure by thinking about how we might want to expose the properties when we're defining a transformation so that other people can reuse it. So if we're going to define an interface for shape inference, we're of course going to do it declaratively because it plays well with operation definitions. If we want to add it to the op, it also allows us to define and generate our documentation like the other declaratively specified entities, etc. So if you look at our interface here on the right, it has a description, but the main part is the set of methods that the interface provides. So these methods have a description on what the method is, but also the C++ return type name as shown here. But it may also have arguments and a default implementation and more, but that's not shown in this example. So once we defined what our operation is, just like in the call example, we add it to our operation and we provide an implementation for it. So by defining our transformations in such a way that the entity that contains the property is responsible for exposing it to us, we can really empower the infrastructure by having all of these reusable components that work well together. In the inlining example or in shape inference, even if we don't expose this pass to other dialects, it's also simplified our own implementation because our implementation of the transformation only had to care about the raw traversal aspects. The actual minutia of doing the inference is the responsibility of the specific ops themselves. So if we look at our previous example, after running our shape inference, all of the casts have gone away and we all have static shapes. So now that we have static shapes, we can think about how we're going to cogen and lower to LLVM. And this is a really important aspect. So we want to make toy executable. But mlir doesn't really have a code generator for target assembly, but LLVM does. And we have an LLVM dialect for mlir, as we've seen, so we have this natural export mechanism. So from mlr's perspective, all we have to do is target LLVM dialect. So let's look at what our pipeline is right now, what our compilation stack is. We have a toy language, and that generates our toy AST, and then we've added our toy IR dialect. And we've used some components from mlir, such as the inliner, but we've also defined our own shape inference. So now we want to lower to the LLVM dialect because we have a natural export to LLVM IR. So we could do the natural approach, which is to just lower directly from toy to LLVM, very similar to what many other infrastructures have done. It would be infrastructure. It's not infrastructure to infrastructure lowering, but it's still kind of this monolithic lowering. So we don't really want to do that. It's really important from an mlir perspective to do partial lowering or progressive lowering. And this means that we don't do very large drops in terms of abstraction level. We want to take a high level abstraction and go bit by bit, progressively lowering down to the level that we want to eventually get to. And the advantage of this is that we can take advantage of all of these different levels of abstraction because many of them also have their own trade-offs in terms of optimization or analysis that we could take advantage of. So if you're going to lower toy IR, a lot of our computations for toy, such as our transpose, our multiplication, they map really well to loop nests. And we could target these affine loop nests that already exist in mlir. So if we lower to those in a combination of standard, just kind of a misnomer, but the standard dialect contains operations similar to what LLVM does from a high level. We could do some high level optimization on our affine loop nests. So things like loop fusion, loop unrolling, these various different optimizations that work really well at a high level that we might not necessarily get to the same effect if we were to drop directly to LLVM. So it's important to note here that we're not lowering everything to affine and standard. We're only lowering computation. So we'll have a few operations that actually remain in the toy dialect at the same time as all of this is happening. So in this example, we'll keep print in our toy dialect. We won't lower that to affine because we could try and devise a lowering from a print to a loop nest, but leave that to some printf library. So we've lowered a combination of our operations, to affine and standard, with some of the toy operations remaining. So we're going to get to LLVM now. So we'll lower the rest of our toy operations, which is print, and our affine loop nests and the combination of standard to LLVM dialect. But the reality of the situation is that this is not actually what happens. What happens is more of this graph. So even affine has progressive lowering to different abstraction levels when going to LLVM. It doesn't necessarily do optimization at those levels, but just having the various levels of abstraction that you can target from a lowering perspective makes these lowering implementations much, much easier. So for example, this SCF is a structured control flow dialect. So it has loops in a very similar form to the affine dialect, except for they don't have as many constraints. So that means the SCF dialect, its loop operations can be targeted by more dialects than just affine. So that makes the lowerings much more reusable. And then those high-level loop forms we lower to the standard dialect, which has this branching, like branch, conditional branch control flow, which has a natural mapping to LLVM. And then, of course, our print operation in toy will also have its own mapping to LLVM, in which case we'll use printf. So if we want to actually do these lowerings, mlir provides an infrastructure known as dialect conversion. All this boils down to is an infrastructure that really excels in converting a set of source dialects into one or more legal target dialects. And target here is, it's a bit of a iffy case, because a target dialect may contain a subset of the source dialects. It may be the same dialect as the source dialect, but have different constraints. So dialect conversion is split up into three largely main components. First is the conversion target, which is the thing that specifies what operations are legal and under what circumstances. The second is operation conversion. And these conversions are DAG-to-DAG patterns that specify how an illegal operation transforms into a legal one. The last is type conversion. And type conversion specifies how to transform an illegal type to a legal one. And if you think about type conversion, our tensor type doesn't have a mapping in LLVM, so we'll have to lower it somehow. And this dialect conversion infrastructure has two main modes. The first is a partial conversion. This is very useful if you don't know about all of the input operations, or if you just don't care. If you only want to lower a subset of your input module, then you can only lower, you'd only have to lower that specific subset. So if we think about how we're going to lower toy to this affine and standard, there are several operations that we don't care about lowering. We don't want to lower the function operation. We don't want to lower the module. We don't want to lower print. They're all fine to just exist in the input. They don't have to be legal. But then there's a full conversion mode. And full conversion mode is really good when you want to make sure that at a specific abstraction level, you know exactly all of the operations that exist there and that they're supposed to exist there. So if you think about the export to LLVM, at that level, we only want the LLVM dialect. We don't want toy, we don't want affine, we just want affine, we just want LLVM operations, because that's what we can export. So that would use a full mode. So if we're going to start defining our conversion to the affine and standard dialects, we'll start with the conversion target. As I said before, this defines what is legal for a specific target. In our case, it's the affine and standard dialect. But it's important to remember here that legality can be dynamic. It could be based on various properties of the dialect or operation, even though it's not shown here. And then there's this concept of explicit illegalness. So for a partial conversion, some of the input operations don't have to be legalized, but they do if you explicitly mark it as illegal. This allows you to know that a specific subset of operations have been converted properly. So for our use case, we want to make sure that our toy dialect has been lowered. We're lowering the computation. We want to make sure that it was successfully lowered, because after this point, we don't want to see it anymore. But the caveat is some operations we still want to exist. So we would mark print as legal, even though the rest of the Toy dialect is not, so that it's preserved. This means that it won't be converted. It'll coexist with whatever else we generate. So we have our conversion target, and now we want to do the operation conversions. So the conversions are a set of rewrite patterns that convert illegal to legal. We use patterns because they're highly composable. There's a lot of reuse between patterns because we can just take them and put them in any different conversion that we want. So if we think about this in the concept of a transitive conversion, we want high reusability. So transitive conversion is where we don't have to strictly generate legal IR. We can rely on a successive application of patterns to make sure that something is eventually legalized. So if you think about the graph that we saw before, with Affine being lowered to a structure control flow, being lowered to standard, then being lowered to LLVM, we would have separate groups of patterns for all of those, and they just compose. So our pass might use them, another pass might use them. Any pass that wants to do this conversion can just provide these patterns. So when we're going to actually write the pattern, specified via the conversion pattern or rewrite pattern class, we'll show the conversion pattern class here. What these take is a root operation type and an expected benefit of applying the pattern. And then they provide a specific method to match and rewrite a given root operation. So for a specific operation, it transforms it into a set of 0 to n other operations, or modifies it in place. So this match and rewrite is a very compact transformation because we want patterns to be reusable. So it'll just take the specific root operation and then generate whatever it needs. So the actual transformations, though, are driven by this pattern rewriter class. So this rewriter class notifies whatever the pattern driver is, in this case, dialect conversion, of all of the mutations happening. And this helps make sure the driver is kept up to date, and then it can perform all of the things we want it to, such as transitive conversion or making sure all of the operations we create get legalized. So we have to notify them when we create them. And after we've created these patterns, we just collect them in a list because we just get a group of patterns and rely on the conversion infrastructure to do the traversal of figuring out which patterns to apply. And this is where the reusability aspect really comes into play, because we can just collect a large amount of patterns that eventually go to where we want and just rely on transitive conversions to get us there. So for our toy to affine, we're doing a partial conversion. So all we do is feed our operations, our target, and our patterns to the driver and let it do the rest. And if anything fails, it'll let us know. So remember, in this case, we're just doing a subset. So we want not all of the operations have to be converted, just the ones that we've made sure to mark. So if we take a simplified example before of our input toy IR, we can do this progressive lowering, do this optimization to affine, while having the toy dialect print operation exist at the same time. So we've done this lowering, and now we have this amalgam of other dialects just growing and living together, optimizing together. And all of this is made possible because transformations can be defined generically. They can operate on properties instead of a hard-coded list of operations. So we can know what our toy.print operation does from the perspective of a transformation without knowing the toy dialect exists at all. So once we've converted and optimized, we want to actually go to LLVM. So only one conversion now is actually necessary for us to write, and that's for print, because we're lowering print to printf. But everything else, all of the affine, all of the standard dialects that we've generated as part of our partial conversion before, they already have conversions written for us. So we can just take advantage of what has already been done, plop the patterns into our rewrite list, and just know that the conversion infrastructure will take care of applying them in the right order to get us to the LLVM dialect. So the actual amount of work that is necessary for us to do this final transformation is very limited. All we are is just collecting patterns together and pushing them through the driver. So this is what really makes progressive lowering powerful. So we're doing this progressive lowering to different dialects, but that's not increasing the amount of work that we have to do. Even at the final stage of lowering, we only need to provide one additional pattern, and that's just for our toy operation. We can make use of everything else that has already been implemented. There's no additional work for us. So after we've actually exported or lowered to the LLVM dialect, we can do the mapping from LLVM dialect to LLVM IR with one simple function call. So now at this stage, we can actually execute our code with only doing the amount of work or less than we would have to do traditionally. So I'll pass it back to Mehdi to handle the conclusion.
All right, thank you, River. So we haven't shown you everything today. MLIR is getting fairly large, and there are lots of other features. For instance, the path management is fairly interesting and includes some nice evolutions over LLVM. We haven't shown you the diagnostic infrastructure. We haven't shown you how your dialect can identify new types and attributes. There is a declarative syntax to customize your assembly format. You can specify canonicalization with each operation, which is a nice other way of approaching the inst combine kind of transformation. We haven't shown you symbol and symbol tables, which is how you can reference a function in a function call. And we haven't had time to get into the heterogeneous compilation pipeline, but we start to have upstream some end-to-end flow to target GPUs with some example that targets CUDA or ROCm or SPIR-V. There was even a GSOC project that was taking SPIR-V as an input and running it on CPU by converting SPIR-V to LLVM using the Dialect Conversion framework that River just showed you. Time to conclude. So MLIR is a reusable compiler abstraction toolbox. It provides really an infrastructure to build IR and transformations. It's easy to introduce new abstraction level. It's easy to progressively lower through the abstraction level. Everything is intended to be composable. And this investment in tooling all along the way has really compounding effect. It makes everything more robust and more friendly to use, and you don't have to walk across bridges that walks across different compilers and different infrastructure, as it's often the case in such projects. The IR design involves multiple trade-offs. It's hard to get it right in the first place. So it's frequently an iterative process. You have to learn, you have to adjust, requirements can change. And MLIR makes compiler design as agile as writing software itself. And so finally, there are also non-obvious compounding benefits to the way you can mix and match levels of abstractions. And hopefully you got a glimpse of that today. And some of the interesting part to me is that by avoiding losing the information too early, it gives us a really fresh new perspective at how we approach solving problems with compilers. And that's it for today. Thank you for attending. We're going to take a few questions. I'd like to mention that we have a very welcoming community. MLIR is mostly present on the discourse forum. We're also on the Discord chat if you like more live questions. We hold a weekly open meeting with every week different kind of topics, either a user of MLIR presenting something or a discussion on some upstream MLIR components. And we try to maintain a bi-weekly newsletter about what's happening inside MLIR and in the ecosystem as a whole. That's it for today. Thank you.
Good morning, everybody, and thank you for joining us for the MLIR tutorial. We are now in the live Q&A session, and we have River and Mehdi here to answer all your questions. Questions we do not get time to during this, we'll answer afterwards in either the Wova community room or on Discourse afterwards. To start off, we have a question from a community. We've asked, is it required to have all operations in one dialect for interoperational analysis, or is it possible to write analysis over operations from a different dialect? River, what do you think?
So I think Mehdi did a great job in the current response in kind of describing what a dialect is. And if you understand what a dialect is, it can help understand different parts of the question. So dialects are kind of just namespaces, as mentioned in the tutorial. So given that they're the unit of abstraction, you want to use whatever that abstraction is. That's what you want to place inside of the dialect. And given that we want to separate dialects out that way, it's very natural that they're going to be intermixed. Actually, you can't even use your own dialect without intermixing dialects already. So to write an analysis that's interoperational, different dialects is something that you'll already be doing if you use module. So if you create an mlir module, you're already doing this, or if you use the built-in function operation. So doing interoperational analyses is already something that's very ingrained in the system, given the nature of how dialects just naturally intermix together. So that's one aspect of it. Understanding that dialects are meant to be intermixed at the core. The other aspect is so from that perspective, you know what dialects that you're writing an analysis on. But there's also if you are intermixing with operations that you don't necessarily know about, or your analysis library doesn't want to depend on. So from this perspective, things like interfaces or traits allow you to kind of understand the properties of the operation that you want to know about without actually depending on the dialect library itself. So this is kind of one of the core philosophies where we have these generic transformations and analyses. So things like CSE or sparse conditional constant propagation or inlining, all of these are generic that work on many different dialects. These dialects compose together, and the transforms library doesn't actually depend on any of these dialects. So there's many different facets that you can do interoperational analysis between dialects. So it's just important to keep in mind that when you're constructing a dialect, you have in mind what abstraction you're targeting, and don't get bogged down on how this is going to interact with a different dialect, because it's just natural within the system. Thanks.
Thank you. So another question we have is, are regions simply basic blocks? How are they different from basic blocks? Mehdi?
Yeah, that's a very good question. So regions are actually a list of basic blocks. You can think of a region as, for instance, in LLVM, the closest equivalent would be the body of a function, which is a list of basic blocks forming a CFG, a control flow graph. And so the specificity of region is that they group this basic block together in a way that SSA value cannot escape. So they create a scope by doing so. And regions are always nested under an operation. An operation can have multiple nested regions. For instance, we model the affine if operation, the conditional, that has a true branch and a false branch as two regions. The true branch is going to be one region, which with its own list of basic block, and the false branch is going to be another region, which is its own CFG. And so we create this scoping like this, which forces a single entry point and a single exit point somehow to the control flow.
Nice, thanks. Sorry?
No, I don't know if River has anything to add to that.
Oh, no, you did. That's a great job. Nothing else on that.
Awesome.
And so perhaps a little bit of a design question in a way. So when you're defining an operation, when would you use arguments and when would you use operands to define the operation? River? So
by argument, I'm assuming you're meaning an SSA value defined by a block argument or an operation. It's just a bit of a misnomer because in the table gen definition, argument can mean attribute or SSA value. So it's important to make that distinction now. So it's kind of a design question for yourself. Attributes represent constant metadata. They're unique in the context. So if your operation has certain properties that are always constant, you might want to just inline those as attributes on the operation itself. But I'd say it's a design question because it's kind of up to however you want to represent your operation. So you might want to take different types of attributes to represent the same constant or different things like that. But in general, it's just whatever is constant on your operation, or that's how it generally works. So the name of a function would be an attribute. It's generally constant. The type of a function generally is, if you think about LLVM, a constant. So, yep.
Yeah, I can add another example, which is if you take operation like a convolution or a matrix multiplication, there's the data that your operation will process, and there are some sort of metadata that's kind of tweak the algorithm. that are just Boolean, or that just an enumeration. For instance, the padding that you're going to apply when you do a convolution can take only 3 value, and you need to have those value at compile time if you want to do a good job at cogen. And so frequently restricting those value to be compile time constants are key to the cogen algorithm and are driven by that. While if they are SSA value, you don't know them until runtime, and you cannot take advantage of this during the compilation flow.
Nice, thank you. So perhaps in this line, I mean, what is the motivation, or actually design, for the introductions of regions in MLIR? You know, why were they introduced?
Yes, I can take this one. A long, long time ago, from a historical perspective, because that's how regions were introduced, MLIR used to have operations and instructions and statements. So all of the Affine dialect that you see now was represented with statements. So this was a completely different data structure to what you see as operations. But over time, we kind of realized that these different data structures aren't pulling their weight, because from the concept of MLIR, we're trying to reduce the amount of infrastructure that we're defining and reuse different components. So when regions were introduced, at that point, the Affine 4 statement had a basic block inside of it, or a list of operations itself. So as a just generalization of that, to make sure that we could represent these things that we already had with one class, we kind of introduced the notion of a block list. And once you start introducing new components, you start to kind of finalize their design or develop them further. So at that point, when we had a list of blocks, we kind of needed to decide what are the semantics of this. And that's kind of how regions came into existence. And over time, as we've wanted to support more use cases, such as functions. Functions used to not be operations either, but we want to support a function body with a region. Or things like data flow graphs. So over time, the concept of region has kind of grown from just list of blocks into what you see now as a region, kind of how traditional projects grow over time.
Thank you. This may be a question for Mehdi. Several projects are growing out of LLVM source tree. Is it possible to use Dialect from multiple out-of-tree projects?
That's a very good question. I think it's less about the design. So from an MLIR point of view, the answer is yes. And there are a good example of that. For instance, LLVM has this incubator project, which is mlir-npcomp, which has a dependency on some part of TensorFlow, on some part of Erie, and manages to mix and match all of that together in a single code base. So technically it's possible. The difficulty is more organizational, because all of those out-of-tree projects will depend on MLIR and LLVM. As MLIR evolve, if those projects are not sync at the same revision of MLIR, it can be difficult to get them all to build together. So it's mostly a question of synchronizing to the same revision and to the same version of the project. But assuming that we follow the LLVM release process in the future, for example, if you get multiple projects that are all you would be using LLVM 12, they would get the same version of MLIR, and you should be able to like mix and match them together or assemble them together.
Yeah, thank you very much. No, I think like this question of almost like setting up a virtual like repository to be able to use these. But yeah, I think like one of the nice things is being able to use multiple different dialects, and also as you showed during this tutorial, how all these interop and lower down was great. Thanks again for the tutorial. We're running out of time for the live Q&A session. We still have a couple of questions unanswered, and so we'll try and answer them either on the session Q&A here, and also please feel free for folks to ask more questions in the discussion room. And of course, there's the Scores mailing forum for any more discussions, and we welcome folks there and in the open design meetings every first day as well. Yeah, thanks, River Mehdi.
Thank you.